we're still back with Matt, the muscle, the laxative, Mashad. Matt, can you read number 15?
A bowling ball traveling with constant speed hits the pins at the end of a bowling lane 16.5 meters long. The bowler hears the sound of the ball hitting the pins 2.80 seconds after the ball is released from his hands. What is the speed of the ball, assuming the speed of sound is 340 meters per second?
Nice. So let's start. What are we dealing with here? We have a bowling ball traveling down a bowling alley, 16.5 meters, and it's about to hit a couple of pins at the end. Now, the total time they give us is 2.80 seconds. But, Matt, is that the amount of time it takes for the ball to travel down and hit the pins?
No, that's actually the sound of the ball hitting the pins and coming back to the person who let go of the bowling ball.
Yes. So, this is the amount of time it takes the ball to travel down the alley, and then after it hits the pins, the sound returns at 340 meters per second to the ears of the bowler. So, what this is telling me is that first, before we can calculate the velocity of this ball, we have to be able to calculate the time that it takes for the sound to return to the bowler's ears. So, this is a two-step process, as usual, like we're used to. Let's start with this. We're solving for the velocity of the ball, and it's a constant velocity, right? What does that mean about the acceleration, Matt?
If it's a constant velocity, it means the acceleration is zero.
Yes, the acceleration of the ball is zero, and therefore we also know that the initial velocity of the ball is equal to the final velocity of the ball, which we don't know. The amount of time the ball travels is also unknown because we don't have the amount of time that the sound takes yet. The distance, delta x, of the ball is 16.5 meters. As for the speed of sound, what's the speed of sound here, Matt?
The speed of sound is 340 meters per second.
Nice. Does it have an acceleration?
The speed of sound doesn't have an acceleration either. That would also be zero.
Right. So therefore we know that the initial velocity of the sound is equal to the final velocity of the sound. And as you said, that's equal to 340 meters per second. The sound travels a distance 16.5 meters. Let's calculate the time that the sound takes to travel from the bowling pins back to the bowler's ear. I'm going to write down our kinematic equations. We have V final equals V initial plus AT. Delta x equals V initial t plus 1/2 AT squared. V final squared equals V initial squared plus 2A delta x. Remember, delta means the change in. And 4, delta x equals V final plus V initial over t, over 2 times t. Matt, which of these equations can we use to solve for the time it takes the sound to travel back to the bowler's ear?
Since we need to include delta x, could we use delta x equals v initial times time plus 1/2 times acceleration times time squared?
Yes, we can. Okay, go ahead and fill this in for me. What is delta x?
16.5 meters.
Equals?
Equals 340
We're going to call that
meters
TS.
per second.
Nice.
Times t plus 1/2 times the initial velocity, which is 0.
No, that's the acceleration.
Oh, the acceleration.
Times
times
squared.
t squared.
Perfect. This second part, because it gets multiplied by 0, is going to 0 out. We can ignore it. This makes our equation 16.5 equals 340 TS. How can we solve for TS? What's the step here?
We could divide each side by 340.
Nice, let's do it. Let me know what you get.
I got 0.05 seconds.
Perfect. And that's rounded. My calculator says 0.0485, but that's a good rounding. Now, Matt, using this, how can we calculate the time that the ball takes to travel down the alley?
So we know that it takes 2.80 seconds for the person who threw the ball to hear the sound of the ball hitting the pins. So we could subtract what we just got, 0.05 seconds, from 2.80 seconds to just get the amount of time it took for the ball to hit the pins.
Right. So, really fast, 2.8 minus 0.05 means that the amount of time it takes for the ball to travel down the alley to hit the pins is going to be equal to 2.75 seconds. There we go. I'm going to replace that up at the top here, 2.75 seconds. And now we should be ready to solve for the constant velocity, the v initial and the v final, of our bowling ball. Matt, which equation should we use from our kinematic equations to solve for v initial or v final?
I think we'd be able to plug it back into number 2.
Number 2. All right, we're taking another number 2.
Good night, everybody.
We have 16.5 equals v initial is what we're solving for. The time the ball takes to travel is 16.5. I apologize. It's 2.75. That's the distance. 2.75 plus 1/2 times 0, because the acceleration is 0 still, times 2.75 squared. But this second part zeroes out because it multiplies by 0. We're finishing up here. We have 16.5 equals v naught of the ball times 2.75. How do we solve for v naught?
So to solve for v naught, we just need to divide each side by 2.75.
Perfect. Can you do that on your calculator really fast?
2,000 years later.
For that, I got 6 meters per second.
Perfect. And that is the velocity of our bowling ball. Great stuff, Matt.